So, okay, so we missed our first talk because of some timing issue. So we rescheduled, and organizers will send you the link for the and schedule for that talk tomorrow. So for this second talk, Subhaditya Bhattacharya from IIT Guwahati will talk about dark matter into different production channels, this freeze in and freeze out through effective operators. So we all know him, so he doesn't need any introduction in this our community. So he is expert in dark matter phenomenology and model building and working for some time. So I hope that young participants will enormously learn from this presentation and part. So your talk will be up to 12:15. So
okay.
After that, so you want to have questions between them, or you at the end you want any question?
So if there is a pressing question, I can take it up in the middle, or otherwise
Right.
we can have a session after the talk.
Okay, very good.
Okay, so thank you. Thanks, Parthuda, for this very nice introduction. And I would like to start by thanking the organizers for giving me this opportunity to talk about my works here in this conference. And as Parthuda already told you, that the title of my talk is Dark Matter Freeze In and Freeze Out via Effective Operators.
So just one second, can you make it full screen?
Surely,
Yeah,
surely. I will make it. Is it visible?
Yes.
Okay, very good. And okay, so we provide a couple of illustrations of this dark matter freeze in and freeze out, and we can take up questions as we go along. Okay, all right, so let's get started. So the first question is, why effective theory? So between am I audible? Is the sound clear?
Yeah,
Yes.
perfect.
Okay, all right. And the slides are also changing, right?
Perfect.
Okay, all right. So yeah, the first question to start with is, why effective theory? Now we all know that physics beyond the standard model is motivated from different observations. And one of the examples that we are going to talk about is dark matter. But we have very little idea actually what kind of BSM that we have on board. So effective theory actually provides a way to gauge the new physics with the low energy fields and particles. So that's an advantage. And second of all, it is sufficiently model independent. However, we will see examples like when we can just build an effective dark matter theory without much prior knowledge of what is the full UV complete model is. While we will also take up an example that where we think of a specific new physics model, but at the same time, when it comes to the dark matter standard model interaction, we do not have a renormalizable interaction, and then we have to rely on the effective operator interaction between the dark matter and standard model. And this is when the effective theory comes into the picture, and we will discuss the consequent phenomenology that comes from there. Now, before we move ahead, let's take a quick tour of what is dark matter. We all know that we now believe that it can be constituted of some fundamental particles with credentials like it has to be dark, like electromagnetic charge neutrality. It has to be stable over the universe lifetime. It better be massive because observations suggest that it has gravitational effect. However, the mass can be of different ranges. And there are actually three main contenders of a dark matter particle, one which is called weakly interacting massive particle or WIM. There is another category which is called strongly interacting massive particle or SIM. And then there is also feebly interacting massive particle or FIM. Now we will discuss one example of WIMP and one example of FIMP in today's lecture. And this can be classified into two main mechanisms to address the correct relic density of dark matter. Now, what is relic density? Relic density is essentially the amount of dark matter which has been inferred from this anisotropies in cosmic microwave background radiation experiments like Planck, which basically suggests that this omega h square quantity, that is essentially omega is what is called the cosmological density, and small h is the reduced Hubble constant. This quantity for the dark matter relic has to be of the order of 0.1. So this is the experimental number that we need to abide by. Now, we can do two different mechanisms to address the relic. One which is called the thermal freeze out, and the other which is called the non-thermal freezing. So I will briefly describe all these possibilities when we discuss the specific cases. Now, there are many unknowns about dark matter. Like, we do not know what kind of particles that can constitute the dark sector, like the spin of it, whether it's a single component or multi-component, whether what is the mass of dark matter, what is the coupling strength with the visible sector. Essentially, the coupling strength with the visible sector classifies the dark matter into the categories which I just talked about. And of course, beyond particle dark matter, there are other areas like, you can have machos, primordial black holes, or even modified gravity to constitute the dark sector, but we are not going to talk about them today. Now, let's come to the point that how do you build an dark matter effective theory, okay? So the basic idea is that unlike the standard model EFT, where you bring the effective operators just with the standard model fields and the standard model symmetry, if you have to build the dark matter effective theory, then you have to explicitly bring in some dark matter particles, because just constructing operators with the standard model fields and symmetry, it is difficult to get the dark matter. And that is specifically because of the added point that the dark sector has to be symmetric under, under different symmetry group than the standard model, because otherwise it will decay. So therefore, this is basically the construct that you add to standard model Lagrangian, the effective operators like OSMDM, which I'm writing. This is constituted of standard model and dark matter fields together, and which has to be, of course, symmetric under GSM cross GDM, which basically means standard model symmetry and whatever the dark sector symmetry that we want to think of. And of course, depending on the mass dimension of this operator OSMDM, we have to adjust the mass dimension to 4 by having lambda with appropriate powers of n-4. So if the dimension of this operator is n, then it has to have a suppression by lambda to the power n-4. And CNs are essentially the dimensionless couplings, which actually sits up front, and these are usually called Wilson coefficients. And most often, at least the examples that we are going to talk today, this operator, which consists which is consisted of dark matter and standard model field, is factorized into ODM and OSM. So this factorization basically tells that this ODM is constituted with dark matter fields. This is an operator which is constituted with dark matter fields, and OSM is constituted of standard model fields. And this crucially depends on one fact, that we assume that the dark matter do not possess any standard model charge, and similarly the standard model doesn't have any dark matter charge, if you have to write OSMDM in the fashion like ODM into OSM as we are doing. All right, and so on top of abiding by the GSM and GDM, under which, so basically now we say that OSM is constituted of standard model fields, which has to be invariant under GSM, while it doesn't have any transformation under GDM. And on the contrary, ODM basically have to have the transformations, or is invariant under GDM, and it doesn't have any transformation under GSM. So it's immaterial to talk about that. And apart, we have to be, the Lagrangian should be Lorentz invariant. This is we all know. And most often this GDM symmetry is the Z2 symmetry. The simplest symmetry that one can talk about is Z2 symmetry, which stabilizes the dark matter. So that's any effective operator at least will contain two dark matter particles. And this is what we will see actually in the examples that I will illustrate here. All right, so let's proceed. So I will give you a quick example that how to construct a simple dark matter standard model operator. So, and we are going to focus here on 2-2 interaction, like there are two dark matter particles talking to two standard model particles via an effective interaction, like the way in the picture I'm showing. And this kind of interaction, so this is what exactly I was talking about, ODM-SM, or which can be factorized into ODM into OSM. And this kind of operator or this kind of interaction with the visible sector actually attributes to all the observables which are concerned for dark matter. Like, you can compute the relic density of the dark matter, which we just talked about. You can talk about the possibility of detecting dark matter via direct search experiments, which is scattering of dark matter from the nuclei, which I will discuss in a moment. And you can also talk about the production of these dark matters at collider experiments. So basically, this is why this construction of these operators like ODMS is important to us. And let's take an example. So this is basically the operator that we wrote. Now let's first construct a renormalizable interaction. That means the dimension of this operator is 4. Okay. Then we understand that if it has to factorize into ODM and OSM, then there is mass dimension 2, which we can attribute to both of these operators. Correct. Now, within the standard model, we know that there are only two operators that we can think of, which has actually mass dimension 2. One is H dagger H, where H is the standard model Higgs doublet, and B mu nu is essentially the field strength tensor associated with the U1 hypercharge. All right. So therefore, if we take the H dagger H, which is the which has mass dimension 2, then we can actually have this operator because there is two mass dimension left to actually construct the full ODM SM interaction. So we can actually attach a phi square to it, and therefore we can have the interaction like H dagger H phi square. Okay, so this phi is, of course, this is a dark field and this is the dark matter rather, and this gives rise to what is called the Higgs portal interaction. So this is one of the simplest and perhaps the most exercised dark matter model that people have talked about. So phi can be a dark matter for you, but however, you need to ensure that it has no electromagnetic charge, and that is possible that if you assign 0 hypercharge to phi and make it a singlet under the standard model, which we all have been talking about, that it doesn't have any transformation on the standard model H group. And next comes the stability of this dark matter. What is GDM? Now, simply you can say that this is stabilized by a Z2 symmetry, so that phi going to minus phi, this transforms like this, and therefore phi square is invariant under GDM or Z2 here. Okay, so this ensures that you will only have terms like H dagger H phi square and not terms like phi H dagger H. These terms are forbidden. Okay. So this is how you can construct different operators. So this was the construction for a renormalizable case with mass dimension 4. But now you can take up, you can construct OSM, you can think of different ODM and just have a marriage of these two to construct higher dimensional dark matter standard model effective operators. So, so once again, if you consider the GSM to be the standard model gauge symmetry, which is SU3C cross SU2L cross U1Y, then you can, so this table essentially summarizes all the possible interactions that one can think of when you think the dark sector to be constituted of scalars and fermions. Okay, so the first example, which is in the notation of the paper, is mod of phi square phi dagger phi. This capital phi is a scalar dark matter, which we introduced in our notation. And sorry, capital phi is the standard model Higgs, which we just wrote in the previous page as capital H. And this small phi that you have is essentially the dark field. So therefore, this is the dimension 4. And then as you can see that you can go to other dimensions um, like you can also have phi square psi bar psi, where, this capital psi is a fermionic dark matter that you have. And once again, you demand them to be gauge singlet, having stabilized under a Z2 symmetry and so on. So in this way, you can construct the operators in dimension 5, you can go to dimension 6, and so on and so forth. Okay. So, well, the explanation of this notations are like this. So OSM here that you see, this constitutes of mod of phi square, etc., etc. So once again, I'm sorry, this small phi is essentially the standard model Higgs, and capital phi, anything which is in the bold facet, is essentially the dark sector fields. Okay, this is exactly what the notation is. Okay. And this is essentially, this table is obtained from the papers of Zankowski, Utka, and Dukt, and also in a paper from Messias and Utka. And recently, we also have written a review on the effective operators, including the dark matter interactions, which is this particular reference with Jose. And of course, there are many other references where DMF EFT has been discussed. Now, basically, in the rest of my talk, I will basically focus on two operators. One is this B mu nu X mu nu phi, and the other operator will be this J mu SM J dark mu, okay, where J mu SM is essentially constituted of psi bar gamma mu psi, and similarly for the dark sector is the same. Okay, so we will come to. Yeah. Yeah, please. Is there a point, comment?
In dimension phi, there is this operator mod phi square phi q.
Correct.
So how it is allowed under G2?
No, it's not allowed under Z2. It has to be allowed under Z3.
Oh, G3, sure. Okay. Thank you.
Yeah. Okay. All right. Shall I proceed?
Yes.
Okay. All right. Okay. So, yeah, just to tell you a bit of historicity, this first attempt of building this kind of dark matter was done by this team: Goodman, Ibe, Rajaraman, Shepard, Tim Tate, and Haibo. And they actually considered the standard model to be the low energy theory, which including U1 electromagnetism, essentially SU3C cross U1 electromagnetism. And then you can essentially construct all the operators which just have the form like chi bar gamma chi, F bar gamma F, where F is standard model fermions, including quarks and leptons, and chi is essentially the fermion dark matter that one can think of. So these are the big list that was provided, and it is one of the most cited papers in this particular context. Okay, so before we move to the specific model, let me quickly go through the phenomenology, like the thermal freeze out, what exactly it does in the context of weakly interacting massive particle. So in this particular example, we assume that the dark matter had sufficient interaction with the visible sector so that it could be in the equilibrium with the thermal bath. And then the evolution of the dark matter number density is given by the Boltzmann equation, which reads like this. This is n psi is essentially the dark matter number density. And this n psi dot plus 3h n psi is equal to minus sigma v thermal average, where v is the molar velocity, into n psi bar minus n psi equilibrium into n psi bar equilibrium, is essentially the Boltzmann equation that one needs to solve, assuming that the annihilation or the depletion of dark matter is occurring from psi to or psi bar to xx bar, okay, where x is in equilibrium in the thermal bath, and the number density is given by therefore n psi equilibrium. So this is the basic Boltzmann equation that one has to solve. And this can be recast in terms of the number density in co-moving volume, which is called yield, which is N by S, where S is the entropy density, and X is basically the ratio of the mass of the dark matter to the temperature. And you can rewrite this equation in terms of dy dx, blah, blah, blah. And instead of n psi square minus n psi equilibrium square, now you have y square minus y equilibrium square. And basically, you can also rewrite it in terms of gamma, the interaction rate, which is sigma v thermal average multiplied with in equilibrium. And this then gives you the equation can be recast in the form of which I have written, like x by y eq dy dx equal to minus gamma by h, y by y equilibrium whole square minus 1. And one can clearly see that there are two limits of this particular equation. When gamma is much larger than h, then these dark matters are in equilibrium, that is y is equal to y equilibrium. And for gamma much less than h, this actually freezes out. So once you solve this equation numerically, this is essentially the picture. So this falling curve is the equilibrium dark matter distribution. And this is the point where actually it departs from the equilibrium distribution to have a fixed, to have a flattened distribution in terms of y versus x plane. This is what we call the freeze out, okay? And depending on what is the rate of interaction, the gamma is larger in the towards the bottoms. So basically, it means the larger is the interaction of the dark sector with the standard model, the smaller the number density or the yield becomes after it freezes out. So therefore, it basically says that your dark matter relic density for this beam freeze out will be inversely proportional to the annihilation cross section of the dark matter to the standard model. And so if you solve the Boltzmann equations, this roughly gives you something like 2.4 into 10 to the power minus 10 GeV to the power minus 2 by sigma V. That basically tells you that if you have to get relic density of the order of 0.1, then the annihilation cross section better be of the order of weak interaction cross section, and that essentially gives the name that it has to be, it is called weakly interacting massive particle or WIM. Okay, so this is basically the this thing. So similarly, or rather on the contrary, if we think about film, which gives you an alternate mechanism for the dark matter production in the early universe, we basically assume, on the contrary to WIM, that the interaction of the dark sector with the visible sector is very feeble, so that it cannot be in thermal bath in the early universe, but it can be produced from particles in the thermal bath via decay or via annihilation or scattering, whatever that you say. So this is a cartoon of that you have thermal bath, and then from that, due to this feeble interaction, you are actually producing the dark matter, which I'm calling X. Okay, and the Boltzmann equation for this particular example is exactly similar to what we have written, that if you now think the process is reversed because you are producing your psi dark matters from the equilibrium thermal bath particles like X. So then what you actually drop, that you drop the yx from the previous Boltzmann equation, and the Boltzmann equation just reduces to this one, that you just see the number density is being built up proportional to y chi equilibrium square, and it doesn't have y chi square as it had for the wind case. Okay, and if you solve it once again numerically, this dotted lines actually will show you that this is how it freezes in. So basically, the number density builds up from this scattering or decay, whatever, from the thermal bath particles, and it accumulates to the point that after to the point when the temperature of the bath becomes actually smaller than the mass of the dark matter, because then it cannot accumulate any further, and then it stabilizes, and that is what it is called freezing in. So this is essentially the freezing in procedure compared to the freeze out what we showed. So there is an important distinction between WIMP and FIM, that for freezing, the production is proportional to this thermal average of annihilation, and therefore it is proportional to the coupling of the dark matter standard model interaction. Like I'm writing it, it is proportional to lambda square. For freeze out, it's actually the other way around. If you remember, this was inversely proportional to sigma v thermal average, proportional to therefore the coupling of the dark matter standard model interaction. So therefore that gives you these two major distinction between freeze in and freeze out. For freeze out, the couplings can be of the order of 1. I mean, of the order of 1 is a rough this thing, but for freeze in, this has to be way below if you have to address the current density. So therefore, that's where the distinction lies. And because in the freeze-in procedure, this dark matter standard model interaction has to be so feeble, the possibility of direct and collider search is limited, although not completely ruled out. Okay. So once again, some of these plots which I have taken is from this phenomenal paper by this Jean-Marc Russell, West, and Lawrence Hall for the freezing. Okay. So let's now come to the example. Is there any question at this moment? Okay, all right. So let's move to the first example that I wanted to quote. So this is a paper with Bashobendu and Bogdan Sankovsky, and this is
okay. I think in the chat there is a question.
Okay, but maybe the chat, if there are questions, then we can take it later, right?
Okay. Okay.
All right. So, so let us talk about this possibility of a feebly coupled vector boson dark matter in effective theory. So basically, what is the model? So we essentially have the standard model, which is extended by a gauge group like U1X gauge group, and there is also a Z2 symmetry that we have to assign. Now, why this additional gauge group is required? Because we want the gauge boson of this additional gauge group to be the dark matter. So basically, we have three additional fields. One is this capital phi, which is actually a scalar singlet. Now, this also has its Z2 transformation. It goes to phi goes to minus phi. The X is, of course, the vector boson, which is the gauge boson under this UX gauge group. And this also transforms under Z2. Where S, that is also transforming under this U1X, but it transforms like S goes to S star under the Z2 symmetry. Okay, so with this actually, so as I just said, that S transforms under U1X, and it basically acquires a vacuum expectation value to break the standard model cross U1X into standard model spontaneously. Okay, and also at the same time, what it does that it makes the dark matter massive via the vacuum expectation value of whatever it attains. Okay, proportional to Gx, where Gx is basically the gauge coupling. Now we also have V phi is equal to 0, and that keeps the Z2 intact. Okay, so this is basically the construct of the model. So with this input, you can write the Lagrangian, and there is nothing much in it, where we only note that this d mu s is del mu s minus I Gx is s mu, because s only transform under this U1x. It doesn't have any standard model charges. And the most general scalar potential that you can write involving the scalars that we have introduced, like S phi and the capital H. Capital H is the standard model Higgs doublet that has all possible Higgs portal interactions, excepting for the quartic terms. Okay, and we adjust the mu H square, mu S square, and mu phi square in such a way that both S and H acquire a vacuum expectation value, but phi doesn't. Okay. And so therefore, what happens that after electric symmetry breaking, there is a mixing between S and H, and that basically gives you two physical Higgses. One is H1 and the other is H2, and one you assume to be the standard model Higgs, and the other one is the Higgs beyond the standard model. Now, what we want, that we want this Higgs to be decoupled. I mean, we do not want to see this Higgs at all. So it's very, 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 very heavy. So this is the limit where we want to exploit what this model prescribes. Now you see that if you actually completely get rid of this S field, or rather H2 after symmetry breaking, because you want to make it very heavy, the interaction between X and the standard model is actually no more there. So what you require is that in the limit, that this is precisely what I said, in the limit when the second scalar is very heavy, the dark matter standard model interaction is given by, then you have to introduce an effective interaction. And the effective interaction is essentially the field strength tensor of this U1X, X mu nu, that is invariant under U1X, B mu nu is invariant under the standard model. And however, importantly, you note that X mu nu transforms under Z2. So X mu nu is odd under Z2. So X mu nu phi together will make it a Z2 invariant at the same time. So this is specifically the operator that I actually showed in that table. So this operator is a dimension 5 operator, and this is, so this is, therefore it has to be suppressed by one of the new physics scale capital lambda. So therefore we have a UV complete model, but in the limit when we can completely ignore the presence of the scalar which gets a vacuum expectation value and makes the X gauge boson massive, in the limit that it is decoupled and very heavy, the dark sector and standard model interaction is basically given by this dimension 5 operator. So this gives you, of course, a trilinear vertex, which you can compute. This alpha and alpha prime are essentially C by lambda and C tilde by lambda. We also introduce a term like beta, which is alpha tilde by alpha, but that's our details. So this is basically the vertex, which actually connects the dark sector and standard model. And this is an effective vertex, as you can see. And we are in the limit where we assume that lambda is very heavy, larger than M2. It is larger than the reheat temperature, and that is larger than M pi, and Mx is the lightest particle. So basically, you can say that two particles having the same transformation can only the lightest one can be stable out of those two, because the heavier will decay. So for example, we want the X to be the dark matter, so X is the lightest, and phi, we want phi to decay to X. Okay, so this is how we do. So basically, in this mass limit, X is our dark matter, and we assume this lambda to be large, so that we can assume this X to be a cube-like dark matter. Now there is a question, I think, if I can take it up quickly. Ognibho?
Hi. So
Yeah.
I just have a confusion. So the Lagrangian has two terms, right? X mu nu and X mu nu tilde. So
Correct.
there is no way we can actually map one to other. Like, is this two independent terms, or because?
Yeah, these are two independent terms. As I said, that this C and C tilde will always be your parameters, but what we, precisely.
Okay.
So both are present.
Okay.
So if you write one, you cannot ignore the other, because both are allowed by the syllabus. Okay, all right. So let's proceed further then. And so these are basically the parameters of your model. And then you do the dark matter production. So now you have to do that. What are the processes through which you can produce the dark matter, right? So then you draw all the Feynman graphs. Before symmetry breaking, you have phi producing X and B, and also the goldstones are involved in the scattering reactions, which I just show. And after electroweak symmetry breaking, this B changes to Z and Z and gamma photon, and also this goldstones change into massive Z degrees of freedom and W plus minus. So these are the channels that you actually have after electroweak symmetry breaking. And then you have the Boltzmann equation in terms of reaction density, and that will basically gives you the total yield, which you have to compute like the processes which contribute before electroweak symmetry breaking. Then so therefore that has to be integrated from reheat temperature to T electroweak, and then beyond T electroweak to T0, the present temperature. This is how it will look like. And then the rest are details which we can be ignored for the time being. Now, interestingly, there are two basic limits of the phenomenology that we see. One is the large reheat temperature. When you assume that the temperature from which this production starts happening, that is what we are called the reheat temperature. If it is much, much larger than N, then this annihilation versus decay contribution will show to be roughly of the order of TdH by the mass of phi. So therefore, you will see that the annihilation contribution actually dominates over the decay contribution in this particular limit. And so therefore, the final yield that you actually build will be proportional to the reheat temperature. And so therefore, the dark matter production will essentially be occurring at a very large scale. So the production saturates at a very large temperature, and then it doesn't get altered too much. So this is exactly what is referred to the ultraviolet freezing mechanism. It was coined by Elahi et al., and this is how it looks like. So therefore, then you can say, well, in this particular limit, I can actually, subject to what is the choice of my M pi and Mx and blah, 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 I can actually get the allowed region of the parameter space of the model, which actually satisfies the correct Relic density. Then there is another region when you say, well, my reheat temperature, the temperature from which the dark matter production starts building, is not that large. Okay, so T reheat is roughly of the order of mass of the heaviest particle involved in this process, which is n pi. And then you see that this annihilation and decay contributions are roughly the same. And then you can see that this mass effects become important, and therefore the production of the dark matter continues essentially to the scale of the dark matter mass itself. So this is so here when you take TD heat of the order of 10 to the power 4, there is a UV behavior, that there is a bulk of production which accumulates at the very high temperature, but slowly, but the decay contribution becomes important at the later part of the story, later temperature, and then there is another added accumulation as you see here. Okay, if you drop the temperature to even further, like 10 to the power 3 GeV, very close to the mass of the pi, then you see a very typical IR pattern where the dark matter density accumulates slowly, and finally it settles down at the temperature at the scale of the dark matter mass itself. Okay, so these are the corresponding allowed parameter space that you see. Okay, so now I will quickly talk about the dark matter signals at collider. So essentially, if you do not have a Richard dark sector, the signal that you have to basically see is what is called the mono X signals. And the signature is basically you can radiate some X from the initial state, and it can be photon jet or any of the massive gauge bosons. And however, what you have that the dark matters are not detected in the detector. So therefore, that has to be missed, and that gives you a momentum imbalance. And this is what is attributed to missing energy or missing transverse momentum. So let's consider a process like AB going to C, D and E, and let's consider that these D and E are invisible and they are dark matter. Now, how this process looks like? So you have AB collision, they are smashing into and producing the C, which is the only visible particle, together with this D and E, which are actually invisible, which are not recorded in the detector. Now, the missing transverse energy or the missing transverse momentum can be associated to the particles, the momentum of those particles which are actually missed. So you can say that this definition is square root of pxt plus pxe whole square plus pyd plus pye whole square, correct? Because E and B are the particles which the detector cannot detect, right? So this is what the definition of the transverse momentum associated to the missing particles that you are producing in this collision. However, this cannot be measured, right? Because you don't see D and E. So how do you measure this? There comes actually the conservation of momentum, which actually helps you, because this collision is occurring along the z-axis. So along the x direction, your initial momentum is 0. So you can simply say pxd plus pxe is nothing but minus pxc. And similarly, pyd plus py is nothing but minus pyc. So therefore, this missing transverse momentum that we constructed with the pxd, pxe, and pyd, pye can be transferred in terms of pxc and pyc. That is, it is the PT visible essentially. So in the mono X signature, you can simply say that the missing transverse momentum, the momentum that you actually miss in the collider, can be associated to the transverse momentum of the visible particle that you that the dark matter is recoiling against. Okay, so therefore you need some recoiling of the invisible particles against some visible ones, so that you can track what you have missed. However, there are possibilities, other possibilities, which we are not going into in this lectures, where you have a Richard dark sector, which cascade decays into a bunch of other stuffs like leptons and jets and so on. Now let's talk about the specific model that we have a film which cannot be produced, because this vector boson X that we just talked about is too, you cannot produce that because the Gx is very, very small. The C by lambda is very, very small, so you cannot produce them. However, you may note that the phi is in the thermal bath, and you have a lambda phi H coupling, the portal with the phi, the parent particle from which the dark matter is decaying, or the scattering of which is producing the dark matter. That coupling is unsuppressed. Okay, so that can cause, so what you can do, that you can actually produce this phi pairs. Now what does phi do? Because phi is in principle that decays to dark matter plus Z or photon, etc. But as we just argued, that this decay, this decay has a strength which is very, 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 very feeble, because otherwise we couldn't establish the field mechanism as we just said. So therefore, the decay of phi is actually delayed beyond the detector scale. So therefore, you can say, so for a typical 1 by lambda of the order of 10 to the power minus 14 to 10 to the power minus 13 GeV inverse, which gives you the correct Relic density constraint, the length of this phi is of the order of 100 kilometers, which is pretty large. So you basically will miss this decay process, and this will therefore gives you another opportunity to actually probe this model through this monophoton or mono X signatures, if you wish. Okay. However, this decay cannot be infinitely delayed because there is a limit. I mean, we want this decay of phi to be happening before the onset of BBN, Big Bang nucleosynthesis, and that puts a limit on this whole process. So that is what we can do. Okay, so this is, I think, is the phenomenology that I just wanted to talk about, the primary part. I mean, the film. I think I'm delayed too much. Do I have to stop here?
No, you can continue for another 5 minutes.
Okay, so then let me give you a quick this thing that this is another paper that we have recently come up with, which is about actually leptophilic dark matter in effective theory. And basically what we wanted to do is to construct the operators for the fermion dark matter. Once again, what you have to assume that you have to assume a dark matter which are fermion, which do not have a transformation under the standard model gauge group, but it is transforming under a Z2 symmetry. Then you want to write all the possible interaction, like in dimension 5, these are the operators. In dimension 6, these are the operators. Now, out of this, we choose those which are leptophilic operators. We are calling leptophilic are the cases where you do not have any Higgs portal or Higgs interaction or the interaction with the standard model quarks. It only has the interaction with the standard model leptons. So this is the subset which you choose out of that. And out of this, actually, there are only two operators which actually prevails if you assume the dark matter to be a Majorana fermion. Okay. So then with this, and there is an important point which you say that basically you have to think of or take all these operators in equal footing when you do not specify what is the new physics actually that you have on board. So therefore you consider all the operators on the same. Now, then once again, the Relic density is very trivial to calculate. It proceeds via the same mechanism that we explained. You can calculate the sigma V thermal average 2 to 2 process involving this suppression of 1 by lambda square. However, for all operators, you must remember that this is for an individual one like the vector interaction, but for all operators, when you are considering, your amplitude actually is added, and then you have to take the mod square. And these are some of the freeze out cases for some specific values of the Wilson coefficients given some assumption of what the new physics scale is. And then there is this dark matter direct search, which once again I will quickly go through, that we know that dark matter can also be observed from the direct search experiments, where you have the recoil rate, and this recoil differential cross section with respect to the recoil energy can have two components. One is called spin independent and one is spin dependent. And non-observation of dark matter basically gives you a bound on the spin independent cross section, spin independent direct search interaction of your dark matter, and basically that's what we want to abide by. Okay, so this is basically the idea. So from the latest xenon 1 ton, you need to do that. Remember that when we talked about film operator, we didn't talk about the direct detection because it didn't have any, but when you are considering the wind phenomenology, that you actually have to do. Now these calculations are not so for the leptophilic dark matter, because the dark matter you are they are primarily talking to leptons. So that, however, can give you a direct search, but through a loop induced process. Once again, I do not want to go to the details because I do not have the time to do so, but the loop factor essentially brings the direct search cross section down, because otherwise, for example, the hadrophilic operators are very strongly constrained by the present direct search data. So then you actually see the Relic density and direct search allowed parameter space of the models when you take all the Wilson coefficients and operators together, and you see for the hadrophilic case, it is ruled out up to mass of 6.4 TeV, while for leptophilic dark matter, the Dirac case is, MK is roughly of the order of 345 GeV, and so therefore this can be probed in at least 1 TeV electron positron collider, while for Majorana dark matter, the spin-independent direct search cross-section identically vanish. So there is no limit from the direct search that you actually have there. Now, then you come to the collider search after choosing some benchmark points, and you can rely on the monophoton signal. So the differential production cross-section with respect to the longitudinal beam polarization can be written in this part. And then you can calculate it with respect to all the Wilson coefficients that you have introduced in your model. And then the total production cross-section can be written in this particular form. And then importantly, what we see that if you choose all the Wilson coefficients of the order of 1, then the total amplitude for this, or L effective, because you have to add all the matrix elements together, right? I mean, so then you see for both Dirac and Majorana cases, the effective Lagrangian or effective operator looks like this form, like E bar gamma mu 1 plus gamma phi b. Now we all know that 1 plus gamma phi b is basically PRB. So this basically says that this signal cross-section is automatically maximized when you choose right-handed electron and left-handed positron. Now there is a limit experimentally that how much right-handed electron that you can produce and how much left-handed positron that you can actually have in the collision process. But essentially you see that you will maximize the signal for that kind of combination. Now, if you change the Wilson coefficient sign, like you have the CL3 and CL4 minus 1 and minus 1, and for the Majorana case, you have only 2 coefficients like 1 and minus 1, then actually this effective Lagrangian changes, you know, and it gives you a form like E bar gamma mu 1 minus gamma 5 into E for both Dirac and Majorana cases. So which is maximized for the left polarized electron and right polarized positron. So this is an interesting possibility which can be exploited. So these are the plots. And there are, however, 3 important points with which I would like to end the talk with. One, that when you are trying to probe the effective dark matter operators at collider, it is much easier to do it in a collider where the center of mass energy is known. For example, in the lepton collider, because you have to ensure that your effective scale lambda must be greater than the center of mass energy. Contrary to LHC, where the partonic center of mass energy is not known, and because the dark matters are produced in the process, collision process, the invariant mass of the final state cannot be computed also. So ensuring the effectiveness of the theory, validity of the effective theory at LHC is very, very hard. And also the beam polarization helps us to great extent. And then you proceed through the event simulation, and this proceeds via usual technique which all the collider physicists know, which I do not, maybe I will be skipping, and I will come to my summary talk. And I will first say that DMEFT is basically applicable to the cases where we have no explicit idea of what is new physics. And however, we can also have the EFT interactions when the renormalizable interactions are absent. And most of the DMEFT analysis is done in an operative specific way, but to our consideration, when we consider effective framework, we have to consider all operators in the same footing, because otherwise we specify the effective operator. Then when we consider the freezing of dark matter via effective interaction, the UV freezing is limited to very high reheat temperature. That is what was prescribed, but we see that if the reheat temperature is dropped, then it can also be. So then in terms of direct search, we say that, we use renormalization group equations to run down the scale of the Wilson coefficients from electric symmetric scale to the direct search scale. And validity of EFT strictly depends on the assumption that the scale of experiments must be below of new physics scale. So therefore, we say that it is much easier to probe effective theory, dark matter effective theory at ILC compared to LHC. And of course, the beam polarization, the construction of missing energy and missing mass can be helpful to elucidate the dark matter signal. So with this, I will end. And I apologize for the delay.
No, it's okay. Thank you, Subhaditya. I must appreciate you for giving this presentation with lots of clarity. I think for young students, it will very appropriate, and I expect some questions. I think already Kasinath raised her hand. So Kasi, can you?
Hi. Yeah, thank you for the nice talk. I have a question on the first slide where you started discussing dark matter freeze-out.
Okay, yeah, tell me.
The dy by dx equation.
Sorry.
So yes, so actually this gamma by h equation. So the physics argument that we give is that the annihilation, reaction rate is much larger than the expansion rate. So there is supposed to be large number of interactions, so they are bound to be in equilibrium. But just by looking at the differential equation, dy by dx equal to minus gamma by h and something. So if gamma is much larger than n, what is the actually argument that we give such that y has to be y equilibrium?
No, see, you have started with y equal to y equilibrium, right? And then
Yes.
there is a depletion of number density that is occurring via h. So therefore, gamma is, gamma is n equilibrium that is also dropping because n equilibrium involves e to the power minus x into x to the power 3 by t, right? So therefore, it's basically, let's forget about everything and let's just solve this differential equation. And you see that you have started, so that is the main assumption, that you started with y equal to y equilibrium. So initially you had to and fro interaction, but there is one point where you can produce one side, but the other side is halted. So this is how it breaks from the equilibrium, and then in the co-moving volume it gives you a result. So if you just simply solve it in wherever that you want, I mean using your Fortran product, because this cannot be solved using what you call this cannot be solved analytically, so you have to do it in a numerical way.
Yeah, I agree. Yeah, I agree. I am asking because I am also facing this problem. The point is that while solving numerically, we get this particular result, but but if we somehow allow the
no, but this is also not completely out of the box, because you see that there is this number density which is depleting with the expansion with the larger and larger age. So there will be a point where it will be difficult for the dark matters to annihilate into standard model and revert back, right? So you assume that you have a box of particles which are actually talking to each other, and that's how they are keeping it in equilibrium. But when you are expanding the box somehow, so then they are actually moving away from each other. Now that actually decreases the possibility of this conversion into one and the conversion of the other. So therefore, that is how there will be one point of time that it cannot be kept in equilibrium, and the number density with respect to the co-moving volume will become constant.
I completely agree with that. I was just concerned about as long as the exponential part is concerned, this particular the equilibrium part. Just to suppose you start with equilibrium distribution, then just by looking at differential equation, can you tell as long as the mathematics of differential equation is concerned? No,
we can actually do that, Kashinath. So maybe it will be it will be a discussion, because we can exactly also what is called semi-analytically derive when exactly is the point that it will actually freeze out. So you don't have to do anything. You just put all the values of the equilibrium distribution like x to the power 3 by 2, e to the power minus x, etc., and then you start solving the differential equation with y equal to yx. Now your point is when the delta y is actually large, because that is the point when it freezes out, right? So that is the point when x equal to xd, say for example, that you can actually semi-analytically, not exactly analytically, semi-analytically you can do it for 2 going to 2. Actually, we did it for a coupled Boltzmann equation also, at least for 2 cases. So that you can also analytically do and find out when exactly, and you can match them, the numerical solution versus the analytical solution.
Yeah,
so
I think you can contact him after the talk, and you can clarify. So we go to the next question. Monimala has some question.
Yeah, Monimala.
Yes, so I actually have a question and sort of like another comment. So I think somewhere you were showing a plot cutoff scale versus something. I mean, this is towards the end of your talk.
Yeah. Cutoff scale versus something. Yeah, is this the one?
No, just before that. 2 slides before that.
Cutoff scale.
This is slide number 23.
Slide number. Okay.
No, the next one.
Next one. Okay, all right.
Yes, so I think some of the region in your parameter space will also be constrained from lab. I mean, if you consider particularly this cutoff scale so low, isn't it?
Yeah, there is a constraint on, I mean,
monophoton.
Yeah, the very low region. You're absolutely right. There is No doubt about it. Yes, absolutely. Here we just say that this is the region of parameter space which is allowed by the Relic density and direct search. But you are absolutely right that monophoton search from left will cut across the low regions of m chi and lambda. Yes.
Right. And I have a comment, I think, which is applicable for your final slide. I mean, yeah.
Yes.
Yeah. So this, but this is again particularly relevant for the low cutoff scale and whether you consider lepton collider or the PP machine. So if you are considering a lower cutoff, then I think this is true that the validity of EFT is more pronounced for, let's say, ILC with low center of mass energy. But for LHC, then actually you have to look into the full fundamental theory. You may get actually tight.
That is not effective theory.
No, that is not
As you just said that you have to look for full fundamental theory.
Yes.
That basically deviates from the idea of EFT, because in EFT you say that I do not know what is my propagator which connects the dark and standard model sector. Rather, I actually construct all possible operators, just assuming what my dark matter field is and what the symmetry under which it transforms. That's it. Yeah, so that is precisely the comment, that you have to somehow make sure that your lambda, the cutoff scale of the theory, has to be larger than the center of mass energy with which this collision is occurring. Because if you deviate from there, then it is very difficult, right? I mean, you can do effective theory involving other new physics, right? Because there is a possibility, suppose for example you produce TH production, then you say that in the TH, and you consider all the effective operator contributions to that, then you say, well, all right, I can still maintain that because I can see the invariant mass distribution of TH, which actually characterizes the scale of interaction, at least for the bulk of events which has occurred. And if the peak of this invariant mass distribution lies above the scale of your cutoff scale of or whatever the new physics scale, then you say, well, this is difficult to abide. I mean, this is difficult to say that this is followed from the effective theory, because most of the reactions have occurred with a energy, center of mass energy larger than lambda. So that was precisely the point, because for the dark matter, you cannot construct the invariant mass of the final state particles. So that's the limitation that you have. So the only way that you know that if your initial state energy, that is the center of mass energy of the reaction. Yeah.
Okay, thank you.
Okay, next question from the workshop itself. I don't know who is some hand I see.
Hi, it's Abhishek. Sir, can you go to the slide where you have described the model part, the first model?
Yes, correct. Absolutely. Let's go to this is it.
So my question is, you started with the complete theory where you have renormalization interaction, after which you have integrated out H2. From there you have wrote effective operator, and you have calculated the evolution of dark matter, which depends upon the reheating temperature of the universe, right?
Well, I mean, you tell me the question, then I would like.
So my question is, the effective operator is coming from the complete theory, means from renormalization interaction, where it doesn't depend upon the reheating temperature. Why it is so? In one region, it does not depend on reheating temperature, but when I'm integrating out the heavier particle, my evolution of dark matter depends upon the reheating temperature.
No, I think, let me clarify this point. So see, first of all, the first part of the question is not related to the second part of the question. Let me clarify. So if you had the S on board, like the H2 field on board, I mean, you can also think of this to be an equivalent of a Stuckel-Barg mechanism, that that you have a mass generation of a gauge boson X, but you do not know how to do that. That is essentially the limit that we are exploiting, that you have a very heavy scalar which is generating the mass of your gauge boson, but we are forgetting it eventually. Now, in this particular case, if you have that, then the interaction between the dark sector and the standard model has to rely via the effective operator or effective interaction, as we just wrote. Given the symmetry of the model, this is the only interaction that you can have. Okay. So this is the first part of the question. So I think this part is clear. So you are absolutely right. I have a UV complete model, but in the Stuckelberg limit, in the decoupling limit of the very heavy Higgs, I do not have an interaction with the vector boson with the standard model, which I want to have if I have to establish it as a dark matter. So therefore, I have to go to the operators beyond the dimension 4, then invoke this effective operator like dimension 5 that I'm just flashing. Now, the point is, when you are actually talking about the production, then you have a dark matter. Like whenever your mass of the X boson is lighter than the mass of the phi, then you have X boson to be the dark matter. It can be produced from the particles in the thermal bath. Now, because phi has an unsuppressed Higgs portal coupling with the standard model, so it can be in the thermal bath, and I can think that this is produced from this kind of an interaction vertex like phi xb. I can produce X. Now, what exactly the reheat temperature is? So this is saying that, because from where, so let me go to the next slide. So if you see this equation, like when you build the total relic of the dark matter, the integration has to start from the initial temperature to the final temperature, and in between there is a symmetry breaking process which comes into. So therefore you break the integration into two parts, like T reheat to T electroweak and then T electroweak to T0. So therefore, what the initial temperature that you starting your integration with, that is not guided here, right? So therefore that becomes an parameter for your yield that you eventually build in. And then we actually say that suppose if you have a limit, because reheat temperature for us is a parameter, I mean, which we do not have any guidance of unless we consider a cosmological model also there. So therefore we said that there are two limits that we can do this, find the allowed parameter space of the model. In one case where I have this very large reheat temperature, and because if it is very large reheat temperature, then it is the annihilation which mainly produces the dark matter, and that's why I say that your dark matter yield is proportional to the reheat temperature in that circumstances. However, we can also have another limit where the reheat temperature is not that large. So in that case, we have to rely, it will depend both on the reheat temperature as well as the mass of the heavier particle which is generating the dark sector. So that is the other caveat. So the effective interaction here is not directly coupled to the second question that you asked, that why does that clarify the case, or
yes, sir, I've got the point. So another related to that is that the plot which you are showing now, the first plot where you have shown the evolution of chi, where
sorry, which one?
So slide 15.
Slide 15. Yes.
What I can see is that there is two type of contribution, right? One UV type, another is IR type, right?
Precisely. That's what I mentioned, that when your temperature is not very close to the mass of the dark matter, but a little large, so then the annihilation still dominates in the first phase of the dark matter production. But then the decay process later starts become important also, because the reheat temperature is not that large. So that's the first case. But even now, if you drop the reheat temperature even less, so that is precisely the limit which I just described, that this is the pure IR limit, where all the mass dependent phenomena is becoming important and the decay dominates over the annihilation processes. So this is the pure IR, and this is mixed UV IR kind of thing. Yeah.
Then I am correct to say that when mass is greater than TR, then because of the mass that decay, mother particle mass, it is Boltzmann suppressed. Because of that, annihilation is dominating over the decay.
Yes, actually, see, I mean, this is very clear if you look into this decay and annihilation reaction densities, which I should have somewhere in my backup slides. If I may, yeah. So basically, you see that this fast Bessel function, if you look into the reaction, this is square root of S by T, and it is integrated over ds, right? So therefore, you can assume that in the massless limit, there is a huge contribution which actually comes at the high, because this integration goes from S minimum to infinity, correct? So therefore, and this actually K1x actually goes to 0 as x becomes large, right? So therefore, there is a huge contribution in the massless limit from the annihilation processes that actually gives rise to this. However, from the decay process, because there is no integration over dx, because this is just the rest decay. So this is just suppressed by K1 MA by T. So this is precisely what you are trying to say. So that unless the highest temperature of the process which is involved, which is way above, then then only your decay is much suppressed than the annihilation processes. But otherwise, when the temperature is not that large, this decay processes start coming.
Okay, maybe because of the interaction, what I can see for small value of higher value of T, it will go proportional like T cube, right? And the second one, it will go like T square. Am I correct?
Yeah, I cannot offhand comment on that. I mean,
because
perhaps you are right. Perhaps you are right.
K1 root s, because for high value of T, it can be written as 2 by x square. Means then for the cross to 2 process, it goes like T cube, and second one goes like T square. Therefore at high temperature, the 2 process dominates and the decay is suppressed, and for low temperature, my decay domains and my cross section and 2 process goes down. I think that
is precisely, that is very nice. Thank you. Yeah.
Yes.
Yeah.
Yes. Thank you, sir.
Thank you.
Okay, I think another question is there. Rohan.
Hello, sir. So my question is, so in the module part, so can I just explain how this S transforms to A star being?
Acha. Yeah, this is okay. So I do not have a pen and paper, but I can explain. See, what is happening that you have this term like d mu x s mod square. This has to be invariant, right? Acha. Now you see that this d mu s is del mu s minus I gx s x mu, right?
Yes.
And when you take the dagger of it, this will involve star, a star.
Yes.
So just from the last term, you see that if x goes to, you can actually compute it very easily. And there is also a minus I, so that becomes plus I and so on. So it's just the invariance of this d mu x s mod square term in the Lagrangian upon the transformation of x mu going to minus x mu, that you can show that s has to goes to a star if this term has to be invariant under the Z2 symmetry.
So this is the transformation that we demand so that we can build the model. It is not
exactly.
Actually
if you want your S, I mean, which we are demanding here, that because whenever you have an added gauge group like U1X that we have, and you want that gauge boson to transform under an additional discrete symmetry like Z2, like X goes to minus X, then the scalar which is transforming under the same gauge group must transform like S going to a star under that discrete symmetry Z2. This is the main point. So, however, if you do not have a Z2 symmetry, then no worries. I mean, you do not have any transformation. But if your X transform like X goes to minus X under this Z2, then S must go to A star.
So, thank you, sir, for the explanation. And there is one more. So, so you considered the this effective interaction involving phi. So why not with S? I mean, is it not protected by any symmetry? I mean,
sorry,
it's also
once again, repeat the question.
So this F mu nu B mu nu phi term in the effective interaction.
Correct.
So there is also a scalar, right? I mean, S. So what is it preventing from writing?
I didn't get the question once more. Can you make the question more precise?
Yes. So let's say write
a
term like
B mu nu x mu nu phi. The point is I cannot write B mu nu x mu nu. Why? Because of the Z2 symmetry. X mu nu goes to minus x mu nu. So Z2 symmetry prohibits me to write a B mu nu x mu nu term. The only term that I am allowed to write, given the symmetry of the model and the fields that we have, is B mu nu x mu nu phi.
Okay. And so this answer you all have actually discussed. So if I just open up the operator, so what can be the scale of lambda in terms of any other particle mass? So can it be
open up the operator means, I mean, you
So
want to have a new physics interaction, which
yes,
actually
yes. So
that is actually a little difficult because this operator is not a tree generated operator. Any operator which has field strength tensors involved in it, that has to be a loop generated operator. So therefore, the construction of a new physics model which generates this kind of operator is not that straightforward.
yes. So this model has to include other UV complete elements such as any other mass.
Of course, of course, of course. And what I say is the following, that if you have to generate this operator from a UV complete model, I mean, which is decoupled and weakly coupled to the standard model, then it must be a loop generated operator. That's another comment. Yeah.
Okay. Thank you, sir.
Yeah,
Thank you,
I
sir.
don't see any more question here. So is there any more question?
Yes, I have one.
Okay.
So my question is little bit basic, basically. So in the beginning of the slide where you are discussing the formalism, so
Right.
is it safe to say that because dark matter is a very special particle which is stable under the visible sector, so the operator is
Just give me a
factorized?
moment. I have to take up this call. Hello. I'm actually in a talk. Can you call back me in a moment?
Yeah. So in the beginning where you are writing, the formalism part, that we can always write it as a product way, OSM and OTM. So because the dark matter will be always stable from the visible sector, so for any kind of dark matter, I can safely make that assumption, right? That I can always factorize it.
No, I can give you an immediate example. It's just the example with which we usually do the phenomenology. I can give you an immediate example where I can have a dark sector which is not invariant under standard model. Consider the possibility of an inert doublet, inert scalar doublet. Have you heard of it?
Yes.
So that is transforming under standard model, right?
Yes,
So therefore, the operators that you construct is in principle not factorized. You consider a fermion doublet, a vector-like doublet, and admixture with a right-handed singlet, say for example. You have a term like psi bar H tilde chi, where psi is the vector-like doublet, chi is the singlet, and H is your standard model Higgs. This is not factorizable.
Okay.
So there are many examples that you can cook up where your dark sector fields are transforming under the standard model fields, and they cannot be factorized into the way that we are. But here, fortunately, that the operators that we have considered are exactly the way that, as I said, that they are actually, yeah.
But for those examples also, we can do this EFT technique, right? There is nothing to actually put us in a problem, right? Like, let's say for inert doublet kind of model, if I write down now effective operators, I can do all the phenomenology there also.
Yeah, of course. I mean, you have to decide what are your low scale fields and symmetry. That's it. I mean, just based on that, as I just gave you an example, like how do you construct this? You just have to construct those operators and see how does it go. I mean, what are the constituents of the dark sector field? Standard model is anyway known to you, so therefore it's not difficult. I mean, one has to be a little patient. That's it.
Okay. I think, yeah, we had a very long discussion. Subhaditya, thank you very much for.
Okay. Yeah, I'm really sorry. I had to hurry perhaps. I mean, I did put too many.
No, you don't need to be. It is an energetic discussion, and yeah, good. We'll meet again in the afternoon session.
Okay. All right. So yeah, bye to everyone, and thanks to the organizers for this wonderful opportunity. Moniwala is